Okay, so welcome everyone to this new episode of EagleFly The Experimental Debugger. Today we will continue making this awesome debugger, and if you like to follow along, please don't hesitate and be welcome. If you have any questions, post them on Twitter or YouTube and I'll be there to answer. And as well, post them if you liked to on the Handmade Network, which on the other streams I already explained what it is. You just have to log in, have an account, and post the questions on the thread that I posted. So yeah, so let's start with this. And the first thing I'd like to do is to open the project. If you like to, one thing to mention I was forgetting. If you like to, I will post the links to Handmade Network thread, to YouTube and to Twitter on the YouTube channel. Well, probably not the YouTube, but on the YouTube channel, the Twitter and the Handmade Network links will be there posted on each video, so you can easily find them. Alright, so yeah, so let me open the project. So if you remember, well, let's compile. There you go, we compile, and I will open the debugger as well, so we can see where we left off, which, if I do remember, was that we were playing around with the jump instructions, and we already disassemble some jump instructions with some addressing modes, and we should today probably do the same thing, expanding the addressing mode thing just the same way as we did with the move instruction. That probably makes sense. Let me open this. And if you see here, well, we have the output stream, some jump instructions. This is an absolute address in the REX, which is an indirect way of jumping, indirect call, if we can say it that way. This is in an offset, it's a relative address. I'm sorry. This is a relative address, and these are pushes and the other stuff that we already done. So yeah, that's pretty much the thing. So if we go back and we see the test stream on the test awesome, we have a bunch. Well, we just put some other jumps, I believe. Where is it? Yeah, here it is. this is the one that we disassembled. This has a displacement 34, which has a mother RAM itself, you know, a core pointer. This is R13. This needs SIB for encoding, you know. This is ESP as well. It uses SIB for encoding. So I think I'm gonna go. Let's do jump core pointer R13, which if we see on the output stream on the disassembler, let's go to here. And these are the jump instructions. And so the jump with the REX prefix is this one. So we have already the pieces to disassemble this one, so we can just test it and see if that works, you know. Over here, just add it as well. So this R13 is really similar to the REX, you know. It's just the same opcode, so we already have the entry for that. We have a 41, which is an REX, and we have a 65 mother M and a 00 SIP, which is the thing that we expected. So let's pretty much run this and see if that's the thing that we see on the disassembler as well. We begin, we have an REX. We're gonna try to find the opcode for that thing. We didn't find the opcode, so that means that we are on an improper. Well, no, we have FF. We didn't find it. 41 mother and byte. So what was the problem? What table ID? We are on the extension table, and we have a 65 in there. What's the 65? 65, let's see. 0 1 2 0 0 1 0 1. That means that we have a mod of in mem, we have a rec in 100, which that's a must for this case, and we have 101, that is let's see that. Oh, I see the problem. I see the problem. Yeah, we have a bug. Well, yeah, we have a bug, a simple bug, but we have it. And if you guys remember, let me drink some water. I don't know if you guys see the bug right there. You know what's if you can see these two instructions, well, they both have the same FF code encoding. You know, they both are gonna be looked for that kind of thing. But the problem is that we don't encode this as our way to handle the bats. If you remember, is 0 the one that we are looking for. So that's the thing that we found out, you know. So 65 is not the same as is 0, so that's gonna be the problem, you know. It's just gonna not find it out because, well, the value is totally different, you know. So we have to go and find the rec field, which is the thing that really identifies the entry by itself, you know. It's not the modem. I mean, at first we thought it was the modem, but yeah, I mean, technically the thing that identifies is the rec field, yeah. So is the rec field, you know, that we want for it. And in fact, it's not even the rec field, it's everything, you know. Well, yeah, how can we say, it can be like a two-pass thing, you know, like right now we don't have it like that, but we can change that. I mean, the identifier itself is the main outby, you know. We need that because it's gonna tell us the entry of the group, you know. It's gonna define, oh, we have group blah, you know, and E0, the rec field is gonna tell us is telling us which one to get, you know, pretty much. So we have to pretty much follow the same path in that case, you know, so that in here, whenever we added the entry, we added E0, which is not correct. And in fact, all of these has to be changed because, well, they are not the thing, you know. They are not the thing that that's correct, you know. So all of this is busted. This is correct, you know. This is just a thing. But by itself, you know, I mean, this is kind of junky by itself. It's not like the best thing to handle the IDs, and we haven't found like a proper way, or at least we haven't make the time to do it. So probably this is not what we want to do on the future, because it's just not the thing. So let's go to the get mnemonic entry. And if you see here, we got the table ID. This function call is the has the property of defining the group, which table we are gonna look for, and the next step has to be pretty straightforward and just iterate through all of the entries. That's something possible, viable, and the thing, the identifiers can be bigger than 1 byte, that's for sure. We have the rec field. So we probably here and get table ID. Let's see which ones we should change. So for sure we have to change opcode extensions, tables, and floating point extensions, at least for now, because those are the ones that we need to think about it. And sometimes, for floating point we have the whole thing, we have 2 bytes that define the ID itself, because if yeah. So possibly, at least for now, we're gonna have rather a byte, the rec, the byte and the rec, or the byte and the modrem as a whole. And my question here, can we just not think about those things and just have the ID to be the byte and the mod? The problem is the thing that we have already, like we have to, we can have it as a checker, what we pass here. It's not just a main or byte, but the whole thing that's already what we're passing here. And we're looking for, you see here we have first, second, third byte, and this is correct, 0xof38, this is a third, this is a third, and this is abstention table that's telling us, oh, you know what, we got all the groups inside here, that's for sure. And what else we have here? This is abstention table, 2 byte up table, and these are the escape opcodes. This is the 8, this is the D, Well, I mean, probably this is okay. It's not like it's not doing its own job of finding what we want to do with it. It's correct. So probably we can leave this like that, and we can go straight on to here to get mnemonic entry. And is that once we get the table ID, and we try to iterate through it, we want to make sure that we got a right match with the right ID, if that makes sense. So this is not the thing. I mean, this by itself is not gonna work, you know. And for now, I mean, we can just think about the simplest thing possible. Probably is not gonna be the best thing, but you know, one step at a time. You know, the thing that we need, it's gonna show us the thing that we can do in the future. You know, if you don't have idea of what, let's do it the thing that we need. Okay, so the thing we need is just like something like this. If table ID we can make a switch. Why not? Table theme case table and in fact I don't know if we can well we can already I mean that call itself, you know, this one already knows the thing, you know, extension table stuff whatever, and it's telling us the offset. It's telling us the offset. The reason that we are not doing it like sparse in the way that they have it in that way is because we were just trying to compress it. If that makes sense. So you know the thing that they have here in the tables. I'm sorry. Where the tables themselves are a little bit sparse, you know, they have holes in it, and that's where like we were thinking, well, do we want those holes? Probably not. And that was a question that we were thinking about, like, hey, how huge can the tables be? How hard can it be to fetch them? Which is not hard. I mean, thinking about sparseness or not, it's just like, well, you know, it's not gonna be the thing whenever we find it. So, but if we think it about in this sparseness thing way, where we say, hey, you know, we are trying to well, if you think about it, probably leaving it sparse is what we want for this case, because even though it's gonna be huge in the file asset thing, we don't care about that, you know. That was the thing that the first time we thought about it. Well, it was like, well, you know, what if we do it, what if we don't, what if we collapse everything and we don't leave holes? But there's some reasons why not to do that, you know. And is that Intel, you know, I mean, right now we don't understand why they have those holes, but one thing for sure is that they are gonna fill it, you know. If they leave those holes, is because they want to do something in the future where they are gonna fill them. And I mean, I'm pretty new to this kind of stuff, but I mean, I haven't seen like the transition of the opcode tables. How were they in the past, and how do they compare to the present of the tables? You know, what has been the evolution of this opcode table encoding? You know, and you know, that's a kind of interesting question. Like, how does Intel modify this? What was the most recent time when they decided to update the entries by itself? You know, do they make shuffle of entries? You know, so that if we found them right here one time, the next time we're gonna find them here. You know, which, if that's the case, that probably is gonna be, well, I mean, it's not like we just have to it will be the same, I guess. Yeah, I mean, the sparsity, I mean, taking out the sparseness thing and compress it, it's just for file sizes. That's the only thing that it solves, but it adds the complexity when we want to fetch them, which is, the complexity is not that hard. So one good thing about keeping it tabley thing, you know, like the way that they have it here, is that, one, if they just add things, we just have to add them on the place where they should be. And B, it's gonna be faster for fetching it, you know, because we already have the way to do it, you know. It's just doing it the same way as we do it manually, you know, reading the opcodes, reading the rec, reading these things, you know. That's we could say that it's way much faster because we can just go and find it, you know. We don't have to even think about it. We just know that it is in the place that it should be. So that's the nice thing about keeping it sparse as it is here. And you know, probably the size itself is just going to be something that we can keep for the future. Well, it's not gonna be fast in the sense that arbitrarily we're gonna try to find to the entry itself the thing because we are not gonna have packed cache lines. So in the sense of optimization, probably is not the best thing to do. But in any case, I mean, we don't know which ones are the most used, and we don't have a way to find that out. So in any case, we still will be missing the cache because we don't know the usability of it, and it can be just as sparse as it is. So even compacting it won't even assure us that it would be faster. Yeah, that's not the case. Sometimes it could be if we happen to have the same usage cases, like the same IDs, the same main opcodes and stuff. That probably can be. But I mean, if you see real disassemblers, real stuff happening, main opcodes change. Well, right here, this is a testing, so we cannot use this one. But if I just open, I don't know, let me see. I mean, this is gonna take like a little bit of time, but for example, well, this is a nice thing. We have loads, move, loads. Well, this is this is I don't know if this is, I don't know what this is. It has a lot of loads and moves. We have calls, moves, a lot of recs, AB, sits B, 8, 9. Eight B, 8D, repeat moves, F3, A4, C7, A4. Yeah, I mean, this is non-deterministic. I mean, the encoding of the instructions are not deterministic in the sense that the pattern usage and the opcode usage and stuff. So we can make that a thing, at least for now. "48 AB, 8C, 24. We have a bunch of moves. If we wanna like think about what's the most used instruction, we probably can say that the move instruction it is. So I mean, if we think about optimization, we will always have that cache line filled with move instructions or something. That it's probably the thing, because the other instructions are just not that used. Probably calls, but the calls are repetitive use, but they are more sparse in the sense, we have more compression on the moves, because we move from memory, then we move back to memory, we move from memory, we move back to memory, we move from register thing, we move this stack, we move the thing, so we are moving a lot of data information all the time. And since the architecture tends to be that the case, because they need registers for it, so that's why they have a lot of moves. We're gonna have C-trees, but this is CC. This is a fetch register open. Oh, this is a call. This is a call. It's a tiny one, isn't it? It's a tiny one. We are fetch register open. So they have the symbols for the calls. That's good. And this is fetch register operand, the other call. So we have a move, the same pattern from RSP. So here we pop the stack, RSP80, and if we pop the stack, we have RDI on the RSP, so that means that we can move from RSP okay, so we can pop to RDI, and then RDI is gonna be loaded with the RDI, or the return instruction pointer, and then return is just gonna make that for example, in get table ID, we have a lot of jumping. We have move CX, compare, jump no equal. So yeah, I mean that we cannot find it if that's the case, you know. So we have to find a better way to do this. So my guess would be to have the tables be sparse, at least the up ID stuff, and the entries can be collapsed in one place, if that makes sense. Since we know that if we go to table thing, we have if fly up by entry, you know, we can have sparsity of this size, I guess. It's not gonna be super huge. So, well, let's see. Let's do this. Well, you know, I mean, we don't need this sparsity at all. In any cases, we just need to have the ID. Now I think about it. That's all, you know. I mean, we just have to fix the ID stuff. Because the ID stuff is the problem. So what we can have here is just that we can solve it here, you know. We can just inline all this stuff. So we already know how to find it, where to find it. And this is a place that we know that. So let's just do that here, you know. So if we say, you know what, we know that we have that, you know, and we have the main of offset stuff, and we can just use that and have we know here that this is the mod RAM. So we can just say, hey, what's going on here? We know for sure, well, that we are just gonna have For now we just have these ones. mm, so we need that, and we also need um, okay, I'm gonna say yeah. I was thinking, what if we add the values? What if we... The problem is that, well, it's not gonna be a byte anymore. It's gonna be bigger, and probably just the same thing. So we need a bigger ID than just a byte. That's the thing. We need a bigger ID than just a byte. We need 2 bytes, and those 2 bytes can be pretty much the thing that we want. So we can just say, hey, this is my 2 byte thing, you know, and this ID, and this is gonna be main of by well, it's gonna be byte, I guess. something like that. And then we have an ID that we can just go and find in the table ID. So this is gonna be called entry ID, I guess. Entry, yeah. And yeah. And then here it's just gonna be the same. We're gonna full and do, well, and this is this is not the whole thing. This is not the whole story. We have to also, this is only gonna work for abstention tables right now. Escape table like DDD, it's similar, but we need the whole byte, you know. So DD, I mean, if they are DDs and D8s, remember that the mother and byte has to be less than, let me see, we have that, we have that, we have that, we have that, we have that. This is the same thing. Well, I'm gonna leave it that way. These extensions, this is the jump, this is the rhythm for that, this is the programming with thing. I'm gonna use this one. I'm gonna move it towards, do we have encoding or do we lose that part? Yeah, I think we'll lose that, but don't worry. There we go. And I want the appendix be 2527. 2527. And I want to go directly to no, well, actually this is not correct. I wasn't looking for this. I was looking for this. Let me zoom out a little bit. You know, we have scalable instructions, you know, and the scalable instructions tells us that the first byte local from D8 to F, each of these outgoes has a mother and byte. The mother and byte is within the range of 00 to BFH. Bits 3-5 of the mother and byte are used on a knockup extension similar to the technique used for 1 and 2 byte outgoes. So we need the 00BF thing, yeah. So if call table ID up extension table, But in fact, I was like thinking, well, why do we don't do it on the same port here? Yeah, why not? And we just say what you need to say. If we already have that here, second byte equal 0x0 and second byte less equal to 0x how it's called BF, else so if it's like that, it's like this. If it's like this, it's like this. We have the second byte. It's gonna be this is gonna be first byte. This is gonna be second byte, and this is gonna be first byte, and this is gonna be second byte, and this is not gonna be needed. And then that's it, so you can just say, well, we have an entry ID for the opcodes. This is going to be like that. And we don't need this at all, and that's better. And we can just say that we return this as well, and that's it. So in the abstention table, we do the same stuff as here. Can erase this stuff. I can just copy this and go to 1 byte table ID, 2 byte. Well, we have to pass it to all of them, so let's go one by one. Let's go one by one. So probably what I want to say is something like this: unit 16 entry D. And I know it can be a unit 32, but we're gonna keep it like unit 16, so we can just for being sure that it's just that we know that it's that size, so for the first byte that's like that, we don't care about that because the resolution is just that case. So you just have to say result entry entry D equal to blah 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 blah. I don't know how you call this. It's gonna be just first byte shifted by 0. well, no, sorry, is third byte, third byte shifted by 0, which is just there. Oh my god, there you go. There you go. And that's pretty much it. Then for the second byte, this is the same. And then for the this is an extension table, which is just 1 byte thing. So that means that entry D equal to the first byte. Well, I can copy. It's gonna be the first byte shifted by 8, and the second byte shift by 3, and 7 shift by 3 back. Okay. Yeah, why not? And we'll need that. And then result entry D equal entry D. And then we have that. Pretty much that's the case. That's correct. And this is the same. It's the second table ID extension, but this has the OF thing, yeah. And at least right now we don't have the third byte used. Sorry, the third byte with thing like F3 or whatever. So we just can say that the same thing. Oh, we'll need that. We just need that. And then just do that. So we have first byte shift by 8, second byte shift by 3, and 0x7. And then here this is the same. Well, here we don't care at all. We just need the second byte. And we can just fill it in with the OF thing, probably, you know, because that's not gonna do any harm at all, you know, because the IDs are gonna just get fixed. Yeah, so I mean, if we want to do this like a function or something, probably. So that all of them are the same. I mean, all of them are the same size. It's just that is the thing that we include the escape output, so we don't, you know. Which, well, we are not gonna do it. It's just doesn't matter. So we just here care about this, you know. There you go. And then there you go. And here we already did it, is the ones with the double ones. We don't need this anymore. And if it's BF, we have that shuffling there happening. If it's that, we just do that thing. And then if we have a main node table, you know, entry ID, it's gonna be the main node by itself, you know, which is first by. There you go. And then this shows the same. So that's it, you know, we just had to fill that. And if we compile that, let's see what happens. We'll have entry ID. Well, there you go. And here, what's this mnemonic? You can just get rid about that. And then we already have the ID, you know, which is the thing we wanted. So we don't need to do this at all. So let's write that. And then table entry ID. So that's it, yeah. We are not like doing fancy stuff here. Now the only problem here is that now probably I'm wrong about this. Yeah, probably this is hold me a second. Yeah, because I'm shifted in the wrong side, you know, because the second byte is the one that has to go shifted, you know. Well, it doesn't matter. Unless that we just make the same thing when we included it, probably. But just for being sure, yeah, this has to be the least significant byte, you know. And then we have the more significant byte here. And we shift to 3 byte plus this. So I'm gonna do it the other way. So yeah. This doesn't need to do anything here. This doesn't need to do other thing there. This is just a second by. This has to be like this, then so I mean, well, that's the thing. So one thing that now we have to do, of course, is just to do the same stuff on the entry thing, whenever we initialize the entries, initialize the tables, we have to have a table of those things, being properly set, which for now we just do it pretty jankily with this stuff here. So this stuff is gonna be gone now, and we want to pass the stream by itself, so it's a little bit stupid, but well, it's not stupid, but I was just thinking, well, what if we don't use the disassembler itself to encode this stuff, because we pretty much, I mean, this is done manually right now, but this is totally error prone, so we probably want to think about doing this by code, and we already have it. The nice thing is that we already have the code, the code is the same, this is the stuff, we just have to pass the stream, and like we can say disassemble it, as the word might say, without fetching the mother and bytes. Probably we just have to think about the entry stuff, and that will make the thing that we want to do, like encode the entries, get the entries. So we want to have a function call that does that kind of stuff, and that's probably what we should do now, because yeah, I mean we can do it by hand, but it's just not gonna be the right thing. So yeah, so let's start by that. I don't know if we're gonna finish today, but let's just start. So it's gonna be how can I say, this thing probably is gonna stay the same. We just want the same stuff there, but we want to have a way to encode the opcodes to be fetched to the tables, so that whenever we go fast fetch lookup those, we just do it in that way, so yeah, I mean I don't have any good reason not to do it. So we have the tables, so probably what we want to have here is also I don't know how you call it here, You know what I mean? And then this is the same. Here we could say, we could think about doing a copy of the same disassembler, you know, so that we can have this and say, well, you know what, we're gonna have this, all this stuff in a function call, you know, well, this. And I'm gonna copy this, and I'm gonna compress it all. Yeah, it's gonna be a little bit different, but we can just see. I mean, I can just do it here, you know. There you go. And then we can just say that we're gonna have cbyte equal to iStream. So this is gonna be pretty similar. You have to go from the instruction stream to the instruction stream count, which is entry found. And well, we don't need to print it out, if that makes sense. That's what I would say. We just need to find this stuff and encode it. We just care about getting the mnemonic entry, but well, yeah, it's just like that. We don't print it at all. So we can just get rid about that, and then we can say that Okay, my darling. Yeah. So what's the problem? Entry found, isn't it? Well, why not? We have here entry found as well. And then here we have to pass it, yeah. Instruction string can. And this is now the thing about this, I mean, this is just, it has the semantics into it, so we have to do the thing that we want to do with that thing, you know. So it's not exactly the same because we don't want to print them out. We just want to like pretty much skip it all the thing. So that instead of doing all this stuff, where is it? That, I mean, for now we can do it, you know. Probably in the future we can just skip it. We don't want to print the stuff, so probably that tells me that we want to make some kind of nice compression oriented programming here, where we have to separate the printing part from the non-printing part, you know, because that's exactly what we want, you know. We don't want to print anything, we just want to find the semantics and skip them every time. So for example, if we go to fetch memory open, we already started to do that kind of stuff, you know, where we have the printing stuff, you know, the push string to buffer, or all this stuff. Push string to buffer. We can just not do all the stuff. We just care about SIB if we have an SIB stuff, and that's it. So that all this stuff has to go out into another call, if that makes sense. We can make another call that doesn't print anything, or we can have a model function, you know, that it has something like this. Where we say print mnemonics, print operands, go through, and we just pass them all around thing, you know. It's not that bad, you know. It's not that bad. And that would be if we want to do that in that case. Which we can try to do. I don't see no reason why not to. And the nice thing about this kind of system is that we are going to start defining the file system and the entry processor, if that makes sense, so that we use the disassembler to make our own table, you know. I think that's really nice. Such that we just get the entries and we just start filling them all together. Now, I don't know if that's the best way to do this, but it's gonna be the first time to do this. So yeah, I mean, I think it's good. So we can do that, you know, print operands. So we just say, you know what, just don't print stuff. Don't print me stuff, please, because we don't want to. We just wanna have the semantics being worked out. And the nice thing about this is that if we don't get the disassembler right, we're not gonna get the tables right. So it's just we have the two packets joined together, you know. And I think that's nice because if you think about it, it's just like we have the same idea of how do we want to work with a thing, you know, like how do we want to get this stuff, which is the best way to attack it, well, to understand it, you know. And yeah. Yeah, I mean that's a little bit crazy, I know, but yeah. So we just say false, you know, and here as well we don't want to print stuff. False. And the get mnemonic entry probably is the thing that's gonna change, so just call me there, you know, because we don't know what's gonna happen. So let me compile first. I'm gonna just set them on so that each call has its own print stuff there. And later if we see that it's a little bit janky, I don't know, we're just gonna do the other way around. So yeah, well, I don't know what other way around. I mean, a better way to think about it is just that try to take the functions out, but it's not, I mean, the code as it is right now, it's just that it's so much inline stuff, you know, so it's not like yeah, I think it's better right now. It's better this way. Probably in the future we want to start compressing this stuff. So yeah, print this stuff, print operands, let's go true, yeah, and we're gonna print operands equal true. Oh, print operands equal true, then print operand here we don't print operands, isn't it? So you can just see that. And that way it's just the same thing, you know. So so let's go one by one. The getting money entry, I'm gonna leave it to the last because that's gonna change a lot. This is gonna be see, we have a model RAM, and here look at this. This is not a thing anymore, or at least we cannot do this anymore. So we're just gonna leave that out. In fact, we don't need even the print operand stuff because we're already passing the buffer. So if we don't pass the buffer, we can just say that, we can just say this, you know. Where we have the buffer here. Yeah, man. Where is it? Yeah, man. Yeah, we don't need this in at all. You know, we just need to get that rid of that. So we don't need this, and then we just don't pass the buffer, and that's it. Pretty nice. And then yeah, this is the same buffer. This if buffer, we just need to fill this. We just need to do this kind of stuff. Both32 SIB by printed by person, SIB gets blah 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 blah, that is sizing by fetch base register, and then fetch register operan, the sum state, we don't care about the fetch. This is gonna pass the buffer, push string to buffer, and now no, let me see, push string to buffer. So this is more like this. And if we do it that way, over here, we don't need to do this. We just need not to pass buffer at all. And then yeah, the same stuff, you know, happening. And flex, feature and fill. Yeah, I mean, all is the same stuff because we are pushing. Push string to buffer, push displacement. Push displacement is just gonna work the same thing, you know. Just printing, pushing. We can just say that we're gonna have push displacement, I mean, if we want to save encoding and decoding the stuff, you know, because we're gonna we can say here buffer size. Well, I'm gonna leave it this here because it's just simple. and here we don't need this anymore, and the same goes is this. Push displacement, it's not gonna do anything because we don't have a buffer. We just care about moving the context, and that's it, isn't it? We can just do the same stuff. Print instruction, we just don't print it out, and what else was push displacement, fetch raster, and it's gonna fetch now. Fetch raster up. It has the buffer count. This is correct. Well, yeah, because we don't care about the registers. We don't care about going and finding out all this stuff because it's by itself, yeah, it's not gonna be working, and they are not gonna be filled. Well, they should be already loaded by the time they are here, or we can assert, but it by itself, we don't care about the buffer thing. I mean, we just care about this, that they don't have a buffer, and itself, you know, even if we pass through here and we make that the push register name won't work, shouldn't work. Bit info, selection, record type, GPR. Yeah. Yeah, I think we don't have to do anything of that because we already like did it that way. Do we need this? Doesn't move the context, isn't it? Yeah, that's the only thing that we want to make sure about this call. This call doesn't move the context, and that's important. So yeah. So we need to do that. So yeah. So let's see, let's run it. The only, I don't know if we should by itself I mean run this because it's just gonna be bananas, you know, because the one that we care about is the get mnemonic entry. you know, because this is gonna be the ID stuff and stuff like that. Hmm. So when we want to pass the buffer, now the problem is that what's the buffer, you know, or why didn't it mark me the error over there? Or is it initialize table? Do we have a buffer thing? Oh, it's because we're passing here the buffer. So we don't pass the buffer here, so we're gonna kill that thing and just, well, we wanna kill it and say instead, well, we'll need this, nor this, nor, and this has to be the same, of course. And here we're gonna pass, let's compile, so we just find the errors. Pass through, pass through, pass through, and here the same. Here the same. Here the same. And that's it. And then we're just gonna be passing around without printing any stuff, you know, which is what we want, you know, because that's the essence of the decoder, you know, and the encoder, if that makes sense. Because now we're gonna encode, you know, the tables as we want to do. So the iStream is gonna be passed as well. And if we run this like that, you know, well, why not? Let's run it. If we run this and we say, you know, let's enter here, and I'm gonna move a little bit longer. This is gonna be the same. I'm gonna put a breakpoint there. So we have C byte, and C byte's pointing to 41. If we see the stream, yes, it is. The first byte's 41. And we know the instruction string count it's 400, well, 400, which is in hex, to 56 times 4 is like a byte, like 1K. Yeah, it's 1K. So yeah, it's 1K. So it's a tiny buffer. and it's the starting point, you know. So we're gonna get the REX, that's correct, and we are going to do the same stuff. So let's see what happens here. We get a table ID, and we are pretty much disassembling this stuff on the thing. The entry ID is 8447, you know, which is the thing that we encoded in there. So we already have the thing, you know, in there. So we can just fill the thing now, you know. Yeah, we just need that ID, and we need that ID to pass and write it onto the old by thing. So pretty much basically this is the thing that's gonna change. This is the fetcher. Now we have to have the encoder. So if we're gonna find it, well, we're not gonna find it all because we don't have any old by count by by the time we move by here, you know. So we're gonna just go with a null entry, and we move the mod RAM by the size of the by count, which is 2, and return. We didn't find the entry, and we break. Okay, so that's pretty much it. Yeah. So what we want to do is, now we can just start for, and you know, the nice thing about that is that now we can just we're gonna get rid about the error proneness of the thing we were doing before about the IDs, and we're just gonna pass the whole stuff, you know. This assembler is gonna make sure it's gonna be in charge of encoding the tables and decoding the instruction stream in the same way, you know, because there's no difference at all, you know. It's just it has to be the same stuff, you know. So we want to do that. I want to go to get mnemonic entry. Why am I there? I want to copy this. And one thing I can do, well, the first thing I would like to do, of course, is that we already know the table ID that we want to encode. So here I want to say that I want to fill the entry stream, you know. So on init, oh my god, init here, I can say I want to feed all this stuff. All this stuff is gonna be gone, you know. And the problem is that if we haven't filled the entries, how do we know how to parse them? You know? That's a question. That's a question. That's a good question. How do we know how to parse them? We will need to fill them first, which we do right now, but we don't have a match it. We don't want it. We don't know how exactly does the this thing work, because we don't have the match. Before, we were working with the assumption that we have everything laid out by ourselves independently, manually, and that was the reason that it worked. But now that we want to try to automatize that kind of stuff, passing the disassembler as a first pass to the code, the encoding of the tables, we can do that by just, because we want to know that we have a mother M, and the only way that we know about that is that we have a valid entry that we got. So get mnemonic entry has to find out, where is it? It has to find an entry for the next this thing to happen. REX prefixes and stuff, all that work fine, but this part here is the crucial part. If you don't find the entry, all this stuff is just gone. And we have the entries, we don't have the matches. So the problems are the matches. So we can know, oh, when these have the matches, but since we want to make the matches, it's just this kind of infinite loop with what to start with, So, that's kind of funny. I mean, it was not a bad idea. It's just that we don't have the necessary information for making it. It was nice try. Yeah, because then, well, how do we know the mother and by if we don't know if we have a mother and by itself? The way that I think we can do it, one way that we can solve it, of course, is just that to address the entries as they come. Since we have all this information right now, is not in the way that we could solve it. The way we were assuming is just that the orders are the same, so that we just get the entry from here and we just like iterate through it. The caveat for that, of course, is that we have to match it. So each instruction thing, you should have the same stuff. But then what if we have a repetition? So one entry fetches the same entry, sorry, one pass on the encoder fetches the same entry. How do we know that? We don't have a way to know that, and that's the problem. So yeah. So yeah, so I think we're gonna need to stick to the solution that we got before, the jankiness of the buy thing. Let's see. So let's just have the whole thing coded, you know? I mean, yeah. I mean, there's no reason why not to do that. So yeah, let me erase all this stuff. It was a nice try. It's not. It's not. I mean, we were so close, but so far as well. So let's just erase that stuff and need to check the extension code for something. Change this totally use probably we need to know this is yeah. Okay. So the thing, yeah, let's just include everything, you know. So we're gonna go and say on the get entry D. Well, I'm gonna. Jesus Christ, how can I do that? This has to match the thing that we got before. How can I do this? I mean, I want an instruction stream. One way to do it is just to have something like this. This is not a thing, but yeah, my problem now was like I want to know which ones were the ones that we got before and which ones were the ones that we didn't. It's like, oh, I forgot what was it. I mean, I can remember, but it's just that. One thing that we can do to solve that problem is to encode this as bit fill, you know, so that we have this, and then we are just gonna have a series of streams that we pass them, and then we already get the right thing, you know, and we just pass the decoder until we find the thing that we want to get, and that's it, you know. So that I mean, this thing, for example, should be the same as this, isn't it? problem is the size. And since we have variable size stuff, you know, everything's variable here. Yeah, I mean, the thing that I'm thinking now is just how to make an instruction stream that can serve both the coding part and both the encoding part. Since we can just encode everything, well, not everything, but let's say, for example, we have REX, we have FF. The thing will be the match, you see? We don't want to have a lot of entries with the same thing. So yeah, I think I'm gonna do just the manual stuff again for now, because I don't see another simpler way to do it. For example, and we have to go one by one solving 41 FF. For example, here we know this is a mod RAM, but we need the 65 as well, so we need to get that. We just want to know, we just want to have a way to get to the next pointer, you know. So we want to have something. I don't know if this is possible, but because we can have a car pointer blah that we fill it, well, like this, yes. Yeah. And we can say, let me see. So I don't know if I say, I mean, if I have A, B, C, is that possible? So we can do that. ABS. And we can have that. That. Yeah. And so what if instead of having cars we have hex values. And then yeah, that's possible. Okay, so it is possible to have that way. Now the thing, yeah, I mean we can have that encoding. For now, if we want to do the pass relatively to the thing we want, I mean if we want to do the thing that we got before, we can do it with this, because in this way we will always get the pointer onto the place where we got. So if we cannot encode more, we just got to the next pointer and that's it, you know. that's the trivial thing to solve this kind of way. Yeah, we can do that way. And it's just gonna be this stuff, you know. So I'm gonna have 1024, 1024, something like that. And I can say this. I'm gonna say instruction stream, blah blah blah. It's gonna be 1024, 1024. You know, well, we know that the biggest one has to be 15, so we can just leave it that like that. I don't know if we want a bigger ones than just 15, so we can just say 128 for being modest. And when I do that, then we can just do that instead. And yeah, the problem, yeah, we have to do that because this is buggers. We want to have the arrays being done properly. So there you go. So if we do that, we compile, we're gonna have the stuff. Now we have the nice thing about having the pointers correctly, so we can just go and fetch them. You know, we can go pointer by pointer, just moving the thing, you know, and that's nice. It's a kind of bidimensional array, so we can just do that, and we can say, well, you know, then we can pass that bidimensional array to the instruction stream initializer and say that instruction stream. Oh, okay, we pass it here. Okay, so I just want to pass it the one that we have, and and yeah, and this is gonna be, I don't know, array counts. I mean, this is an array of arrays, and it's just that we have a thing. We just need to think about something like this. Now isn't like instruction string 0. This is an array. This is an array of arrays. This is an array with 128. And then 1 is an array with 128 and stuff like that. And then, yeah. So first of all, I would like to see what array count says about this. Yeah. And this of course has to pass that thing. So I wanna say this will have that. Can I pass the pointer? In that case, here I will need to pass this. It's insane, I know, but no, it's not getting better. Okay. So when we pass just a pointer and we have an array, that works because we pass a pointer to an array of things. But now that we pass the thing, I don't know if there's a syntax for that specifically. Do we need a cast or something? You need I mean, it's something like that. Because if we pass the first array, then we can do that and not be problem. Yeah. Now the problem is that if we pass it this way, we're not gonna have the nice thing about how to move the pointer, you know. That's a problem if we pass it like that, because the pointer doesn't know the semantics of how to move the thing. So I mean, if I say, well, I don't know, could I? Probably not. Well, let's test it instead of guessing. So first thing I was like thinking, well, what about array count stuff, you know? So, and what about initialize the table stuff? So let me how can I do this? This is not correct. Well, let's just check that out. I'm not totally sure. So I'm gonna put a breakpoint here. And we're gonna have filling this stuff, you know. We have 128 sizes, so it's gonna be a little bit sparse, but that's it, you know. And well, haha, haha, my bad. So count is 1024, so he got the first one, and that makes sense. That's nice, you know. If I say array count 64 0, array count 64 1, count 128 128. So yeah, that's correct. It's totally correct. So what we can do here is, because it's taking the size of it, and it's taking the size of each one of the 128s. Since it's size, it's gonna be correct, yeah. So yeah, that's nice. Yeah, I mean that works. And then so we can do this, yeah. We can just pass this, then There you go. You can just leave that out. And we just pass it. Now instruction stream, it's just a pointer that is gonna be bananas, isn't it? Instruction string counts, it's correct. Let me see. Yeah, 1024. So let me see if I can find it on the well, let me put up here a thing. So instruction stream, let's see the memory, and yeah, it has the string 41FF65. And inside there, and then here's the next one, FF is 0. I don't know why do we have that thing. Yeah, because we just pass the pointer, we don't pass the whole set of pointers that we want to pass, you know. So for now I'm gonna say that I'm gonna put it inside, because why not? Why not? So if we do it that way, then what we can do is just to do the same thing we were doing before. Let's try it now one more time. Here comes the second round. Let me go to init, and I'm gonna move this on the same place we got before. I'm gonna move this a little bit down before, so we can just keep it that way. And then we can just say that we're gonna pass over 64 under array count, instruction stream 64. Don't care about that. And then we just need a pointer, and here it's not gonna be exactly the same. We can just get rid about all this stuff. Well, in fact, we don't need this thing. We can make our own again, because yeah, it's gonna be a little bit simpler if you think about it. Well, we can keep the skeleton of this and just say, you know, we can just get rid of that, and I don't wanna skip them, I just wanna add them. So I wanna say that I don't even want a context. We don't need a context here, so we can just erase the context. We don't need the buffers by themselves. We are thinking on the operation mode. Yeah, we're thinking on the operation mode. We're not even thinking about the operation mode at all. We can just erase all this stuff. Are we thinking on the operation mode here? Is it relevant? Is it not? I mean, it is. It's not. No, it's not. I mean, the entries have their thing, you know. So this is not relevant. So yeah, there's more operation modes. I don't care about that. Flags. I don't care about the flags. Check if we can have more than one material prefix. Check if we can, I don't know, a material prefix to material prefix. So the thing that we want to do is pretty simple, you know, like I want to have a unit thing here, sig by and here, well, c by equal to and here, even here is different. and then we can say that we're gonna push that by, and then we're also gonna push the same thing. We can just keep pushing until we know, but yeah, we're gonna keep the semantics, so yeah. We don't have a context here. So we probably want to have a context, since that was the way we were doing that. Yeah. Well, we don't want a context. We just want the base. And the byte count. And that's it, isn't it? So that means that we want to decouple it. I can say if I don't know if we already have this. Well, no, EagleFly bit fill. So we want to have here and this can be pretty rudimentary, I guess. We don't need anything about this, we don't care about that. And we don't need this context here, we don't need this here, we just need to push byte. And here we're gonna copy the things we need. So we don't need anything at all, but just we want to have this get table ID call here as well, and then that's it, isn't it? Assert table ID invalid. You can assert as well, it doesn't matter. And this is, we don't need that, this is specific to this call, and that's it, isn't it? So we can just get rid of this and say, you know what, get table ID, we wanna use get table ID, and get table ID basically returns us a table ID which gets the entry ID. You know, the entry ID is not, I mean, it was the thing that we thought we can just include, but I mean, we don't see any problem. Oh no, my bad. No, yeah, no, I was wrong. Yeah, we cannot include everything because the other stuff is optional. You know, the only thing that is a must is the main of byte and the rex field or whatever it notifies. You know, so we cannot include everything because the other stuff is optional. You know, so yeah. I was wrong about that. So we cannot use the bit field by itself. So it's just we don't need this. So bit field can go away. So we just need to get to the place, it's just like, well, whatever. We don't even need to push anything here. It's just like yeah, the thing we had before. And here it's just byte stuff as we had before, and then here it's just the same, and here it's just the same. Don't care about the REX at all. And then we just get the table ID from the CBY stuff that we want to assert that this is the main by all the time. So yeah. And then we can just say that we wanna, the table ID, that's all we care about. So we're gonna get the main by entry ID thing. The way we encoded it, it was like, what we want. We have 3rd byte or 4th byte or whatever we need there with the font shifting. So we say table entry ID equal, and we're gonna start filling out the stuff that we got before. So this stuff is gonna go away. We don't need it anymore. It can just go away. And pretty much all this stuff, we have to fill this out ourselves now. So we wanna make sure that we match it correctly to the entry index, which is gonna be that's gonna be the hardest part, I guess, among the things, because we don't remember how was the thing done. We just move it like 1 byte table, 2 byte table. I mean, it's not like a mess, but it's just we're gonna need to find it ourselves. That makes sense. How can we do this easily? So we have this stream. We got the ID from the stream, and we want to match it with an index of an entry, or an entry, whatever. So what entry it is, we don't know. We have to go back and see each one of them, if that makes sense. Well, we have the stream here, of course, and we can say, oh yeah, this was a whatever stream. I think we have it on the disassembly. I don't know if we copy that here. We didn't. That's too sad. I mean, we want also the opcode bats. If we got the copy, if we have copy the opcode bats as well, that would be nice. Which probably we want. Well, we don't need the opcode. We're already matching it. I mean, we have the add. I mean, we have which one is this? This is a jump. I don't know. This is a jump. Here we're missing the jump REX thing and a jump R13, and that's it. So we have the matching. Now we can see here. So let's do it. Jump R13 has to go with index something, you know. So this one, this ID here is gonna go with the index something. So I need another panel here. I'm gonna leave that here, and I'm gonna need this one here. Alright, so here I'm gonna do CPP disassemble, and then right here I need, can I move this a little bit? There we go. Perfect. I need here to move, and I can keep this like this. Well, yes. Right here I'm gonna play around with this. So I got the entry ID, I need an index form, and I'm gonna copy this stuff here. And I need to get the up by index here and fill it out correctly. So we can keep these like that. The only thing that we want to make sure is to fill this in an order, you know, so that we have, I don't know, something like ID table 1024, and we're gonna fill it out. ID table and index table entry. So that's it. That's it, what we want to do right there. Pretty simple stuff. I don't know why we have this under. This can be erased. I'm not going to erase it right now. I'm just going to keep it right here, and then I'm gonna keep this just by now, because this has an up by count, and the up by count has to match the size of the entry count. See? So yeah, I'll leave that there. And then I have a table, I fill the table, and then here I wanna do the same stuff, but instead of using the up bytes, I wanna use table ID and the up by index, the same thing. Yeah, that's pretty much the this thing, yeah. Oh, it's called ID table, my bad. So it's just confusing with the ID tables until ID table, I can call it code ID table. Yeah, here we would just need to do the same code ID table. And this is opcode index. There we go. And then now this is assuming that they are in the same order, that's why we're just adding it in the same order, which is not the case, of course. So one way to solve it is just to rearrange this stream so that it has this kind of thing. That can be one solution. Or another is to rearrange. I mean, we have to rearrange one or the other. The stream, this one, this little one, or this huge thing that probably we don't want to rearrange. Add entry. Yeah. Add entry. So probably we want to rearrange the streams, It's just the simplest thing to do. So the stream has to match these ones, or rather it has to be these ones, okay? So we have to go one by one from here, from the add entry, and put the add entry that corresponds to that thing, okay? I think we just have one add entry, which is this one. So add by pointer, blah blah blah. So this has to go on the topmost bar in the encoding. So it has to be, I don't remember which one was. It's 1 2 3 4 5 6. 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. This is a floating point instruction. This is an add. Oh, okay. This is the add. This is the first one. Oh, okay, but that wouldn't solve the problem at all, isn't it? Because yeah, because of the repetition stuff. Repetition. So we have to be more clever in this. We just have to think about how to add them in a more sane way, We already have a way to like kind of decode and have the get table ID easily from a trivial instruction stream. So how can we trivially get the entry itself? one way I mean, like to pass the whole stuff there. So one thing we can do, and probably this is gonna be a little bit crazy, but one thing we can do is this. And right now, I mean, this is probably not the thing that we want to do on the end, but we don't care about the time that this takes longer to do because it's just not the thing, you know. So we want to have a matcher here, which before was the index, of course, but now we have to have something more that just tells us about this thing, you know, like probably even having something like this, you know what I mean. Probably want that. And the whole of data information. It's just gonna be passed as well. Yeah. I mean, yeah, my solution was to just iterate across the whole entry stack and just have the match, you know. We already have a way to generate the ID. We just have to fill it in all the places that we need to fill it in. Now, my question, I was like, well, do we want that? Do we want this part right here, you know, this section right here to be like our table generator, which basically, I mean, I'm thinking that we are writing right now, because it's like we are starting to make the table generator just do the stuff that we want to do, you know. Like we first got the ID from, you know, like an arbitrary string, you know, we get an ID and we just have to make an entry for that ID that we have, you know. Yeah. Yeah, I think we're gonna need to think a little bit more thoroughly how to make this. Yeah, I mean, this is a tougher thing to do, you know, like the table generator. Yeah, because we don't have the information right now. We don't have the complete set of information that we would like to have, so that we can automatize this kind of stuff, which would be kind of nice, you know. But it's just that we're missing an important part of information. So I think, I mean, I'm gonna try to do it manually back again, so we can just return the stream here to a normal state, which it couldn't be harder. So we can just say, you know, I'm gonna put do here, and then do which, I mean, probably the automatic is not the word, because we still have to do all these things manually. Yeah, the entries have to be filled manually. I mean, at least from the place where we are right now, you know. If we want to make that automatic, that's a problem, you know. So here we have the order. We have 1 byte IDs. We have 03. 03, it's here. 03 is the first add, you know. It's an add instruction, which is the only add that we have, isn't it? And it's a 1 byte, so all these are the same. That's good, because that's 1 byte. These have to be, now I'm gonna change this to union 16 the odd bytes to 56, and yeah, this is the same. This is 2 byte IDs, so this is gonna have the same 3 bytes. The problems are gonna be the abstention tables and stuff, so we solved the problem a little bit less, but yeah. So let me go to abstention tables. Here we go. They are 3. Yeah, they are 3. The first one is the VM resume. Okay, so we have the VM resume here, and the VM resume has an encoding of is a number 1, 2, 3, 4. So if we look at here on the instruction string, it's 1, 2, 3, 4. So it's this one, OF 01 C3. Okay, so it looks like that is the thing. And I know, okay, this is the mother byte and this is the main byte, so we need also O1 to be passed there, like that. And in the way that we are encoding it, it's the least significant bit is the first byte, and the most significant bit is the second one, the most significant byte, sorry. So it has to be C301. And what else? Where am I? Yeah, we're on the bin resume. So we have C301. Yeah, that's correct. Now it's not C3. Yeah, remember, it's not C3. It has to be O1 and then the C3, but the rect field, only the rect field. That's only we want. So the rect field for C3 is, let's do it manually. So we have C, that means that we have 1, and we have this, and then 3, that means that we have a rect field of 0. That means that this here is 0, 0, 0, 1. Okay, and then this 40 is add entry 1, which has it's an add entry with abstention table. Okay, so the add entry with abstention table should be this one, isn't it? Is the other add entry, because yeah, this is the first add. The first add didn't have an extension table, so it has to be this one. So it's number 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. So this is the 8040 F0 OB, and we are looking here at the 40. That means that, yeah, this is the mother byte and this is the 80 main byte, and we have 40, and then we have F0, which can be, I don't know if it's where is it? Yeah, it has to, oh no, F0 is a displacement, and its OB is the immediate. Okay, so we just need to think about 80. So we have to have, well, X0 is the one that we have to encode the whole thing. So here, this is not that, is 0x80, and here we need 40. We need to think about 40 in hex, which is fine. It's just 0, 1, 0, 0, and then 0 0 0. So we have this, so it's also a 0 on the rack, yeah, so it has to be 0 0 on the rack, and then 80, and then the last one is a jump entry 2, which is the last one that we did, which is, well, right now we don't disassemble the jump 13, but yeah, it's jump REX, I believe, because it has a mother iron byte, but it has the extension table, so it has to, yeah, it's 4 to 64. It has string blah blah blah, operation 64, yeah. So it's this jump racks. So it stays 0, so that means that it has to be here somewhere, and it's this one, yeah. This is the jump R13, so yeah, so it's this one right here. So we have an FF, so this is the main byte. We want to have that here as well, the FF, and the E0 has to be the thing that we had before. So E0 is just 1 1 1 0 and 0 0 0 0. That means, I'm sorry, we have 1 0 1 0 0 0 0 0. So we means that we have 0 0 1 0 0 0 0 0. That means that we have 1 2 4 8 16 32 32 value, which is F10 is 16, to 0 is 32, isn't it? So to, where is it, calculator, yeah, to 0 is 32, so we need 32 there. Sorry, 20 FF, and that's it. So now that's correct, or at least we think that's correct. We have to test it, and then we're just missing 3 now, which are the floating point ones. So we just need the 05 thing, and the 05, let's go to this cable table thing. First we have a FLD entry, which we just have, we have it here, FLD. We're looking for the DD first. Yeah, this is the DD. Okay, DD. It's an FLD, which is in 1 2 3 4 5. It's in 5. So we have it here, so it's in 1 2 3 4 5. So this is the DD, and yeah, it has a DD as we might expect. It has an 05, which is the thing that we encode on here. So we're missing the DD, and this DD, it's only the rec field, because the model RAM is in the range between 00 and BF. So DD has to come first, as we know, DD, and then 05, it's not gonna be 05 anymore, it's gonna be 00, because 5, I mean the model RAM byte, if it's 5, means that it only uses the first 3 bits. So the next 3 bits, which are bits 3 to 6, well, Yeah, I mean indexing. Well, if it starts from 0, it will be the third and the fifth. But whatever, are all 0 because that's what 05 means. And then this. So it's 0, 0, 0, DD, and then E1 has to have also DD, and this it's the modern byte. So we know that E1 is 1110 and 0001, and that tells us that we have a 1000. That means if we mask the thing, we have a 32. That means that we need a 20 in here. And then for the C1, that means that we have a D8 in the bottom part, and we have a C1 on the mod RAM. Oh, hold me a second. No, my bad. Yeah, because E1 is on the other range, so we need to encode the whole thing. So E1, we need the whole thing, so E1 is correct. Okay, and then C1 is on the topmost part, so we only need to encode that way. Okay, yeah yeah. And that's it. And that's it. So right now, we needed to do it manually because that's the way sometimes it goes. But we are not defeated yet. We have to find a way to make the tables. Of course, we haven't got to the place where we are ready to make the tables, but don't worry about that. It shouldn't be that kind of hard, if you make sense. We just have to find a way. That's the way it goes all the time. So we have C1. Yeah, it's C1. BF. Yeah, that's correct. So we have D8 on the thing here. Yeah. And just for making sure, we have a FUCOM on the other side. FUCOM, it's on the index 1, 2, 3, 4, 5, 6. We'll find it here is 1, 2, 3, 4, 5, 6. It's a DD E1. That's the reason why we have the E1 there, and that's why we used the E1 there, and we put the DD at the place. And the other is just the D8 C1, and that's it. The same thing that we've got before, which is a fat entry, and the fat entry is on the 7. 1, 2, 3, 4, 5, 6, 7. So we say 1, 2, 3, 4, 5, 6, 7. Yeah. So we have the 8C1. Perfect. So now that we solved that problem, we can just say, well, let's do it. So we use that as it is, we use the old bytes, and now we can just copy down in the same order we had it before. I'm gonna move this on to the topmost part, so it's in the same place as we got it before, and this has to change to odd bytes. Yeah, odd bytes. Odd of code index. Yeah. Yeah. So now let's solve all this stuff. What's the problem? IBase is not a member. Oh, okay, so let me change that on the disassembly. Yeah, we don't need the field, so we can just move this back like that, and it's called iBase, and I don't remember what was the name, so let me see. I by count. Pretty brilliant, my friend. And I can just do it like that, and I can erase that. Alright, so let's test this because we don't know what's gonna happen. For reals, we don't know what's gonna happen, so for reals, we don't know what's gonna happen. So let's just initialize the table, and let's just in fact, I'm gonna well, it's an R13, isn't it? Well, let's just do it because that was the that was the instruction that we wanted to decode at the first part of the string. Okay, so let's just do it. You know, let's just go with the flow and initialize this. We got an rex, we don't care about that. We move it around. We got for the mnemonic, and let's see what the table ID. Oh, we already get the table ID. You know, let me see what we got here. It's an 8447. Let me put it on hex so we can see it better. It's 20FF. Do we have that encoding? We should. I don't know. Let me see. Init. Yeah, we have a 20FF. Oh. Yeah, we didn't trash it. Perfect. Okay, so there you go, and let's try to find it. It should be the third. There you go, we got an entry now because we solved it. And perfect, we got the entry. Let's see the entry and the context as you might think of it. It's a jump instruction that's totally correct, and we can just play around with it. You know, we got an entry found. Go and fetch a memory operand. In this case, it's an R13 memory operand, so we can just what's going on? Mother and by it's 65. Is it 65? Let me move here. Yeah, it's 65. So the thing, oh, it's because we have an SIB thing. Yeah, we have a it's a memory thing. I don't remember. No, well, I can put it in the test as what did we do there? Yeah, we have a, oh, it's a memory operand. Okay. Okay, I was like, what's going on here? So it's gonna be the displacement, push string to the buffer, SIB by person. It should have an SIB, isn't it? Or am I looking it wrong? Let me see the mother M. We have a 65. That means this one. No, but this is SIB. We have a 65. 65. It's totally weird. Why it's 65? 65. It's, we don't have even a, well, yeah, we have a displacement, but it should be 64. Yeah, it should be 64. Why do we have 65? Do we copy wrongly? It has to be 60. Well, it's R 8, 9, 10, 11, 12, 13. Oh, no, yeah. Okay, that's totally weird. Okay, no. So I was just getting confused. Yeah, this day has been a little bit harder for us. So whatever. So yeah, there's no SIB. We fetch the register open, and we see the buffer is R13. Yeah. It's like what? And yeah, we're gonna have yeah. And oh yeah, okay. My bad. So we print instruction, and yeah, jump R13 normally. Yeah. Perfect. So yeah, the whole stream was interesting. That's what I would say. Where does the SIB the I can move that, I guess. I want to see bytes. It's FF. We are on FF. What FF it is? Oh, okay, so yeah, we're on the next one. Okay, perfect. There you go. So we got a stream back. We got our stream back. And now we disassemble another instruction. Let's just to finish this, I want to compare it with the output stream. Where is it here? So let's. We have jump RAX, we have jump R13 is a new one, jump 00015 115, jump FFF8, push R12, push RAX, move SPL RAX, move RBX R13 RAX times 2, move RBX RBP plus RAX times 2 plus 000, move RBX RBP RAX times 1 FFFF, move RBX RAX times 4 110, RBP RSP times 12 R plus R12 times 8 R10 RA R12 RA R14 R8 RAX plus displacement 003222210 RAD RAX 0032210 RAX RDX RAX FFF0 OB FAT ST0. Oh my god, what happened? Where's the other set? Where's the other part of the stream? We have FUCOM, we have FLD, and we don't have BM resume. So it didn't find the BM resume one. So we have a bug. So let's fix that. I was like, yeah, everything's perfect, but yeah, the BM resume is an abstention thing. It's nice because the FUCOM are correct, and the FLD and the FAT, but the BM resume is the one that's missing. So the BM resume, let's put a breakpoint there and see what should be the encoding for that. Let's see. So BM resume, if I do remember correctly, well, it's 1 2 3 4. 1 2 3 4. This is the one. We have an OF, we have an O1, and we can put OF and see what happens. And see what happens. See what happens. And well, let's see the instruction stream. Yeah, we're on the OF. And we don't have an REX. Let's try to find it out. So the get table ID, let's see what we get. It comes from the OF. So we're gonna encode that entry ID is 000 OF. Then we have that. On the encoding stream. Which one it was. It was where is the vim resume? It's the first one. So this should be OF. Why it's a 1? Where is it? Oh, we thought, yeah, it's this totally package is OF like that. And the other ones seem to be, I don't remember which one it was. This one, the second, it was an add entry 01, and the add entry it's this one. So we have 80 40 F0. This is the mod RAM, which has to be 00, and this is the main output, so it has to be 0080. Yeah, it's 0080, and then 20FF. I think this one is the one that we already disassembled, isn't it? So yeah, this is correct. So yeah, that was the only problem. Okay, so let's just rewind this. It was a typo. There you go. So now we have our VM resume back. We have a pre-align R. We have an add, which was correct, and we have our new jump R13 thing, which is nice. So yeah, I think that's it. We have add EAX, shield left double EAX 03, PLNR XM0 XM18, VM resume, FLD 004, FOCOM SD1 SD0, SD0 SD1, REXFF0 OP, REX RDX, REX, RAD, and let's just check the whole thing again, whatever. RAD, REX, whatever. R8, REX, oh my god. Yeah, R8, R13, R8, R12, RBP, RSP, R12 times 8, 3210, RBX, RAX times 4, plus 00322110, RBX, RBP, RAX times 1, FFFFF, RBX, RBP, RAX times 2, 0, RBX, R13, RAX times 2, plus 0, SPL, REX, push REX, push R12, jump FFFF8, jump O15, jump REX, and jump this thing, which we can copy, I guess. Oh my god. There you go. There you go. So yeah. So well, let me just compile this. Let me close all this stuff. So yeah, please, if you have any questions, post them on Twitter or YouTube, and I'll be there to answer. Okay. Please make your questions relative to the thing we did today, and I'll be happy to answer them. You can as well post your questions on the Handmade Network forum. And yeah. So I would say, please, thank you very much for coming, and I will see you all on the next stream. Okay. Take care.